Welcome to the Deep Dive. Today we are exploring a truly counterintuitive finding from the world of AI. It seems sometimes the smallest, simplest model is actually the most effective. We're diving into sources showing how tiny neural networks, ones with just a handful of parameters, are using deep recursion. And they're solving these hard puzzle tasks that, frankly, often stump the massive large language models. Our focus is on benchmarks like ARC-AGI, which is designed to measure, advanced reasoning. The big players, models like Deepseek R1, Gemini 2.5 Pro, they still seem to hit a wall here. And why is that? Well, their architecture mostly relies on autoregressive token generation, which means basically one little mistake early on in generating the output, it risks poisoning the entire answer. Even with expensive add-ons like chain of thoughts, code, or extensive test-time compute, TTC, LLMs just haven't managed to reach human-level accuracy on ARC-AGI yet. That risk of cascading errors is just, well, it's too high.
Yeah, that performance ceiling for the LLMs is a big part of why the field started looking for alternatives. And the predecessor to the model we're looking at today was the Hierarchical Reasoning Model, or HRM. HRM was interesting because it took this biologically inspired approach. It used recursive reasoning loops combined with deep supervision, and it really proved that a dedicated, smaller model could navigate these complex puzzle environments where the huge models were failing. So our mission today is really to unpack the successor model, the Tiny Recursive Model, or TRM. TRM basically takes that core idea of recursion and just strips away almost everything else. It dramatically slashes the parameter count, gets rid of the complex theoretical stuff, and crucially, it achieves much higher generalization across benchmarks like Sudoku Extreme, Maze Hard, and both ARC-AGI 1 and ARC-AGI 2.
Okay, so let's start by digging into how complex that original HRM architecture actually was. Because understanding that complexity really highlights what TRM managed to fix. HRM, it was a supervised learning setup, right, using two separate small networks, phi-hour and tel-dollars. And you set around 27 million parameters.
Yeah.
Built around this sort of high-low hierarchy,
Sure.
recursive reasoning, and deep supervision.
Exactly. And that hierarchy, well, that was really the source of a lot of the theoretical and computational headaches. HRM's forward pass, how it actually processed information, was quite involved. It needed multiple recursions, maybe 6 function evaluations, sometimes more. And it used these 2 latent features, segs and 12 These were meant to represent different processing frequencies, kind of loosely borrowing ideas from, theories about how the brain might handle information hierarchically.
Right, these sort of biologically inspired ideas. But they led to compromises when it came time to actually train the model, didn't they? Especially with calculating the gradients.
Absolutely. The first big mathematical hurdle was just dealing with the depth of that recursion during backpropagation, for learning. To try and save on memory and computation, the HRM researchers used a kind of mathematical shortcut based on the implicit function theorem, or IFT. Now, this theorem basically let them estimate the gradient by only backpropagating through the last couple of recursions. But it only worked if they could assume the function had reached a stable state, what mathematicians call a fixed point.
Ah, okay. So they were trying to skip some of the expensive calculation by just assuming the system had sort of settled on the right reasoning path already, like calling it done too early.
That's a good way to put it. And, well, that assumption turned out to be pretty shaky in practice. Analysis showed that when they actually applied this one-step gradient approximation, the required fixed point, it was unlikely to have actually been reached. The latent features, denials and suboptimals, were often still changing quite a bit, far from converged. And if the system hasn't stabilized, that shortcut gradient they calculated isn't just an approximation. It actually risks messing up the learning process.
That sounds like a real problem. A potentially great idea, recursive reasoning, but kind of tripped up by the difficult math and the instability it caused. What was the second major cost factor built into HRM?
That came from their adaptive computational time mechanism, ACT. Now, ACT itself is a smart idea. It's designed to let the model figure out when it's done enough reasoning and can stop early, which, should speed up training. And HRM's implementation did halt early, averaging less than 2 steps instead of its maximum of 16. Sounds efficient, right? But here's the catch. The way they implemented it relied on a Q-learning objective, and to calculate the loss needed for that objective, essentially to decide, should I stop or keep reasoning? It required 2 full forward passes through the network for every single optimization step during training.
2 full passes. Ouch.
Yeah. It essentially doubled the training cost, all for the promise of maybe speeding up reasoning time later. It made the whole training process pretty computationally expensive.
Okay, so HRM definitely showed promise on these reasoning tasks, but it sounds like it was overly complex, mathematically a bit unstable with that IFT assumption. and quite costly to train because of the ACT implementation. That really does set the stage perfectly for TRM. So how did this tiny recursive model manage to avoid all that complexity but still get the deep reasoning power?
TRM really represents well, a radical simplification. The researchers essentially, throughout the biological arguments, they ditched the complex hierarchy. And they went back to basics, ultimately landing on a single tiny network, just 2 layers, and they started by fixing that gradient tracking problem.
Okay, how did they get around the IFT issue without just, losing the ability to learn deeply through the recursion?
They just avoided needing the implicit function theorem altogether. It's quite straightforward, really. Instead of assuming a fixed point was reached, TRM defined the whole recursive process, say, elaboration ends of the reasoning network. And then it simply backpropagated the gradient through the entire sequence, all other steps. The whole thing. This completely removed that unstable assumption. It provided a mathematically solid way to train the model. Yes, traditionally that would be memory intensive, but because the network itself was so tiny, the memory cost of this full backpropagation was actually manageable, and it was far better than using an inaccurate gradient. They also streamlined those latent features. Remember the Lawlers and Sepal from HRM?
Yeah, the high and low frequency ones.
They simplified them. The high-level one, Sepal ones, basically became an LEODU, which is just the current proposed solution or output. And the low-level one became Sepal A, representing the latent reasoning trace.
Wait a second. If the goal was simplicity, why keep 2 separate features? Zalos and Yael. Why not just one?
That's a great question. It turned out keeping them separate was actually pretty fundamental for maintaining the depth of reasoning. The studies showed that if they didn't pass along the current solution state, then the reasoning feature suballer had to try and store the solution itself, which wasn't optimal. It cluttered the reasoning. But conversely, if they didn't pass along the previous reasoning steps, the model effectively forgot how it arrived at the current proposed solution, the step-by-step path, and that led to unstable outputs. So maintaining that separation, one feature tracking the reasoning, one tracking the current answer, was crucial for deep, iterative problem solving.
Interesting. Okay, let's talk about the size again. You mentioned they went down to a single network, just 2 layers. That seems to fly right in the face of the whole LLM philosophy of bigger is always better. Was that 2-layer decision just like an accident? Or did they specifically find that was the sweet spot?
Oh, it was a very deliberate finding. It came out of extensive ablation studies they ran. They swapped HRM's 2 medium-sized networks for this single, drastically smaller one. And the research clearly showed that using only 2 layers actually maximized the model's generalization capacity.
Maximized it. So adding more layers hurt performance.
Yes, exactly. This is the core insight, really. Adding more layers decreased generalization because the network started to overfit the limited training data they had.
Wow. So the solution to a really hard reasoning problem wasn't just throwing more parameters at it. It was building the simplest possible network and then relying on deep recursion to get the needed computational depth.
That's precisely it, especially when data is scarce. And remember, for tasks like Sudoku Extreme, they might only have around 1,000 training examples. Small networks that rely on deep iterative recursion seem much better at avoiding that overfitting penalty that often hits larger, shallower models hard. You get the computational depth you need, but without inflating the parameter count to a point where it just memorizes the training set.
Okay, and the final piece of this simplification puzzle was sorting out that inefficient ACT training.
Yeah, and that fix was simple and quite elegant. They just removed the Q-learning continue loss objective from the ACT mechanism entirely.
I cut it out.
Just cut it out. And that immediately got rid of the need for that expensive second forward pass during training. But, crucially, it still managed to maintain reliable accuracy for deciding when the model should halt. So the training process became much faster and easier to implement without really sacrificing the benefits of adaptive computation time.
Okay, let's look at the payoff. What did all this architectural simplification actually achieve? The parameter efficiency alone seems pretty staggering. You said TRM-AT, the one with self-attention, uses 7 million parameters, compared to HRM's 27 million.
Yep, 7 million versus 27 million.
That's nearly a 4-fold reduction for what you're saying is a demonstrably better model.
And the performance gains really tell the story, especially on the toughest benchmarks. Take Sudoku Extreme, TRM-MLP. That's the version without self-attention. It achieved 87.4% test accuracy.
87%. Wow. What was HRM scored?
HRM was at 55.0%, so that's a massive jump. Huge. It really highlights how much stability they gained by ditching that unstable IFT approximation.
Okay, what about Mazehar? That involves larger context.
Right, 30 by 30 grids. On Mazehar, TRM at the attention version reached 85.3% accuracy. Again, significantly higher than HRM's
But
74.5%.
the real test, the benchmark everyone talks about for reasoning, is ARC-AGI. How did TRM fare there against the giant?
Well, TRM performed strongly on ARC-AGI 1. It hit 44.6% accuracy, which was an improvement over HRM's 40.3%. But the most, shocking comparison is on the extremely difficult ARC-AGI 2 benchmark. There, TRM had achieved 7.8% accuracy.
Okay, 7.8%. How does that compare to HRM?
HRM scored 5.0%. So again, a noticeable improvement.
And the crucial question, how does that 7.8% stack up against the huge models, the ones billions are being poured into?
This is where it gets really interesting. That 7.8% accuracy from TRM it beats some of the major players. For instance, a massive model like Gemini 2.5 Pro, even when using lots of test time compute, only managed 4.9% accuracy on ARC-AGI 2.
Wait, so TRM, this tiny model, running on presumably much less power,
Much less.
it actually surpasses the performance of one of the world's largest, most expensive models on a car reasoning benchmark.
That's what the results show. It's a pretty significant finding for the sort of small model approach to reasoning. It's also worth noting an architectural trade-off that came out of this research, linking the model choice back to the type of data. The TRM version without self-attention, TRM MLP, did best on tasks with a small, fixed context, specifically those 9 by 9 Sudoku grids. But for tasks with much larger context lengths, like the 30 by 30 grids in Mazehar and ARC-AGI, the TRM version with self-attention, TRM generalized much better.
Okay, so attention still matters for handling larger input sizes, even within this recursive framework.
Exactly. It confirms that even in these specialized recursive models, those fundamental inductive biases related to input structure are still really important.
So the story of TRM seems incredibly powerful. You get superior performance, better generalization, all achieved by drastically simplifying the architecture and slashing the parameter count. It really feels like a textbook example of less is more, at least when it comes to this kind of deep reasoning task.
I think that's the big takeaway, yes. You can strip these recursive reasoning models right down to their absolute essentials. Get rid of the shaky math assumptions, forget the complex biological metaphors, and they actually become stronger, faster, more robust. That simplicity seems to be what unlocked the performance gain. But while TRM clearly shows better generalization while being much simpler and more efficient, there's still a fundamental question this research really brings to the forefront, and that is, why exactly does this deep recursion help so much? Why is it seemingly better than just using a larger, deeper, but non-recurrent network? We see it works, but the deep why is still kind of an open question, and that's definitely something for you, the listener, to think about as you watch how AI architecture evolves.